So where does this get applied to real life?
So that would be if you needed to take an integral
Yeah.
in the real plane. So let's say you have a very complicated thing. Just take an integral. It's a little complicated. I mean, this integrand here is a fairly simple construction. It's a trig function over a linear expression.
Okay.
But it can be extremely difficult to evaluate these types of integrals sometimes, especially when you have limits of infinity here. But this is a fairly standard little, I mean, not complicated looking integral you would have in Calc 2.
Okay.
Now, you won't have it, I'm saying you could, just the structure of it. It's not that complicated in appearance. But yet you may need to compute this for some reason. You need to know the area under this curve for some reason. It applies to some physical phenomenon out in the world. So then it turns out you can only evaluate this thing exactly. You can always approximate. You can use numerical techniques to approximate this thing if you needed to. But if you wanted to know the exact answer to it, then you would apply some sort of bizarre strategy in the complex plane. You would create, how to describe this to you exactly? Things we can just do this, just a half plane. So if this thing had some sort of residue here, let's say it did, so then I could integrate around this, and it turns out that I can call this R, call this negative R here. If I end up taking the limit as R goes to infinity, then it makes this enclosed, this simple closed contour here, it makes it extend out and take up at least fill out the entire upper half plane.
Okay.
In the process of that, these two values here are really what's going to be going on here. It's going to translate over in some sense. We're going to make it a complex valued function. Right, we'll make it complex. Z is a complex number. This is all happening in a complex plane over here. Now there's a way you can rig this using Cauchy's integral formula to compute this, and it will cough out your real value function, which would not be possible otherwise.
See?
The main thing that Cauchy's residue theorem is used for, which is also highly related to this construction here, is for the inverse Laplace transform. Laplace transform is used everywhere. In every physical application, everywhere, Laplace transform is used. If you need to invert the Laplace transform, it turns out you have to do it in the complex plane. And so that's where it comes in for a wide variety of physical applications.
Okay.
It deals with Laplace transform.
Okay.
Well, Laplace transform is though usually shown in a first semester differential equations class, which is just slightly beyond a Calc 2 class, as far as I'm concerned.
It's very complicated.
It is. It's ridiculously complicated. It's ridiculous. I think people think up sometimes.
What is differential about?
Equations?
Yeah.
It's about solving differential equations. As opposed to solving polynomials, we're used to solving things in the form x squared minus 4 equals 0. You're used to solving something like that, right?
Yeah.
The answer is 2 and negative 2. So you know the answer. So how do you know the answer? You just sort of algebra with it, right?
Yeah.
How, and I'll take square roots, like we talked about last time.
Yeah.
So now we want to solve some other type of thing. Let's say it says derivative of something minus 4 equals 0. Now you have that.
Mm-hmm.
So you want to solve an equation as a derivative in it. That's what you want to do.
Okay.
So in this case, you can play a little bit of algebra because this one's so simple. I made a very simple example. Well, if the derivative of something is 4, it must be that the function y was just 4x. So now I know the answer, or an answer. Could be 4x plus c though, right? Could be anything like that. So that's how you solve the simplest of all simplest differential equations there. But it becomes very complicated when you have, you know, a differential equation like that. So you see, instead of powers on the exponent, right, instead of your exponent being here, you have tick marks. You have the number of derivatives you're taking. So this is the second derivative of a function minus 4 times the first derivative plus 6. equation times the function equals 0.
Okay.
So then you solve something like that, and you end up using techniques that are similar to this, if the problem is simple enough and kind enough. You use very similar techniques that you use for solving polynomials, it turns out. And that's really what you're doing. You're trying to solve something that you want to find a function. Instead of finding a number, you're finding a function, y of x, that satisfies this differential equation. You put it in there, it would make it true. Just like you're trying to find a number here, if you put it in, it makes that equation true. So you're finding numbers, you're finding functions. That's the main idea. Because the way it works in physics a lot of times is you know a lot about the rate of change of something. You know something's changing with time. You know about its derivative. You don't know what it is. So now you have an equation, you have some relation between a derivative and other things you've measured in a lab or something, and so it gives you a differential equation. Equation with a derivative in it. So you need to be able to solve that. So develop the calculus of differential equations to solve all those cases. And so then you can get a closed form function that describes what's going on with your scenario at any time you want. Right?
Yeah.
If I know how fast you were traveling at this particular moment, then maybe we can do something with the equation and figure it out, and maybe I can now tell you how fast you're going at every single moment. Something like that.
Yeah.
That's kind of what we're looking for. Or what position you're at in every single moment. Give their example. There's a whole other branch of mathematics out there that has nothing to do with calculus, though. Right? Calculus schmalculus. You can learn about combinatorics and things like that. Learn about discrete things, not continuous things. 2-4. Anybody have any questions about the homework? I can bring it up real quick if you have any questions about 2-1, 2-2, or 2-3. We can knock those out real quick if you need. Let me know. I have not. I'm going to get to you today.
After class?
Yep.
You said that the online homework is due by the end of the week.
No. The online homework is, you'll have to look online.
It says it's due this Sunday.
Do this Sunday?
Yeah.
Sunday.
Well, it's homework
Right,
and
so
quiz.
you see it's after the test, yeah. You do have some time after the test. I'm not sure how much for each time. Don't anticipate it's a whole weekend every single time. I don't know offhand, I don't remember. But you should just look online and see what the... But all chapter 2 is due at the same time. Quizzes and homework. And then same thing for chapter 3 and so forth. But I don't remember what day each one is necessarily. Anything else?
So let's see. Project 1 says you have purchased some land which you would like to use in enclosure for your pets. As of now, you are only interested in the size of the enclosure as opposed to the design of the inner proportion of the enclosure.
Susan, you're worried about the project, yes?
Yep.
We haven't covered every section yet, though. So you may not know the information you need yet to tackle it.
But you're making it due this Monday.
Right, so by the time... This Monday? Next Monday.
Next Monday.
So therefore, by the time we cover it today and tomorrow, you should have all of the information you need to tackle it. So,
Okay.
so you should ask about it on test day. If you can't figure it out, you know what I'm saying?
Okay.
You can ask that day, because you already covered every section then, by then, you know what I mean?
Okay.
And if it's still not clear, then let me know.
Okay.
But it may be a little too soon to tackle it right now.